大家早上好。今天我们开始我们密码学的第二个报告，然后这一期是比较苦的关于 MPC 的报告。我现在就用英文介绍一下吧。Welcome everyone to the series of lectures on cryptography organized by the Shanghai Key Institute and the Shanghai Key Laboratory for Privacy Preserving Computation. Today, we are very happy to invite Professor Rosulek to introduce the basics of multi-party computation. So these will be 4 lectures, each of 1.5 hours. Today is the first one. Mike Rosulek is an associate professor in the School of Electrical Engineering and Computer Science at Oregon State University. He is the author of over 50 peer-reviewed articles on various topics within cryptography. His main research topics focus on protocols for secure multi-party computation. His work has been recognized by a prestigious career award from the National Science Foundation, as well as research awards from Google, Facebook, and Visa. Mike, you can take over from now.
Okay, thanks you. 谢谢，你好. I want to thank you all for coming today. I want to especially thank Yu for the invitation to speak with you today. Thanks to the Shanghai Institute and the Shanghai Key Lab for organizing these talks. I'm very excited to be talking about secure computation with you today. I'm sorry I have to be all the way in Oregon and you have to be in China. I wish I could come back to China and do these in person, maybe some other time. So, so I have, as he said, I have 4 lectures prepared. They're about 1.5 hours. I welcome you to ask questions during the talk. I have a computer here that I should be able to draw on the screen to answer some questions if anything is confusing. So feel free to ask questions in the chat. And yeah, just please ask questions when you are confused about something. So today I'm going to talk about the basics of secure computation, and we will talk about Yao's protocol, one of the most well-known examples of secure computation. Okay, yes, so I will start by talking about what is secure computation, and I'll spend some time talking about how we define security for secure computation, because that's very important in this area. And then, like I said, I will describe Yao's protocol. It's for 2-party semi-honest secure computation, and that will be today's agenda. So the setting in secure computation is that there are many different parties. They don't trust each other. Each of them has a private input. They would like to use their inputs in some function and learn the output of some function. So in this picture, each person has an input, x1, x2, and so on. They agree that they want to learn the function f applied to their inputs. Maybe the function f is something like an election, an auction. I'll show some other examples of different kinds of functions f that they might compute, but they all agreed they want to compute some function f, and they only want to learn the output of this function f. They don't want to reveal anything else about their private inputs. The parties don't trust each other, so they want certain guarantees. The biggest guarantee is privacy. Each party does not want to reveal more about their input, no more than the output of the function that they agree on. So no more than f applied to their inputs. But there are also some other guarantees that are important. One guarantee that's important is that the different parties must choose their inputs independently. So you might imagine that even if I don't know what x1 is, maybe I could be able to choose my input to be related to X1 in some way that doesn't let me learn X1. Well, we don't want that to happen. We want, I must choose my inputs independently of X1. And we also want the guarantee that if many different parties are getting output, their outputs should be consistent. There shouldn't be some impossible combination of outputs, something that's not possible as an output of F. But the main one is this privacy guarantee. And these guarantees should hold even if some of the participants are cheating, and even if many of them are cheating and they are working together. So that's the main idea. Before I get to the definition, the security definitions, I want to give some examples. So as we are going through these lectures over the next few weeks, you can think of these examples. So I chose several examples that are actual real world examples, and you may have heard of some of these before. So the first one, this is a situation that happens in Denmark. In Denmark, there are farmers who grow beets, a vegetable, and they want to sell their vegetables, and each farmer has a bid. They say, if the price of beets is this amount, then I will agree to sell this many beets. So in Denmark, there's one company that buys all of the beets. So there's many sellers, but only one buyer. The buyer also has some bids. At this price, I will want to buy this much. So these are their private inputs. And what they want to compute is something called the market clearing price. Basically, this is where the supply curve and the demand curve meet each other, and that's an equilibrium for the market. That's the price where the total supply equals the total demand. So this would be a secure computation of the function that takes all of the farmer's bids, adds them up, and then finds the crossing point of these two graphs. And both the farmers and the buyers want to keep their bids private because that's very important for the economics to work. So this is something that has, since 2009, this is actually how sugar beets are sold in Denmark. They use a secure computation protocol to compute the price of sugar beets in Denmark. So that's a very important example for secure computation in the real world. Here's another real example that Google uses. So Google is an advertising company. They show ads to a bunch of their users. Maybe they show an ad from a car company like Tesla. But then when somebody goes to buy a Tesla, there's not always a direct link, like a cookie in the browser. And so Tesla wants to know how effective was this ad at getting customers to buy expensive cars. So Google has a list of all of the people who saw the advertisement. Tesla has a list of all the people who bought expensive cars. And if these were tables in some database, then they would like to learn the result of this SQL query. Basically find all the people who saw the ad and they also bought the car, and then add up all of the purchases that they made, right? So compute the total amount of money that you could attribute to these ads. And this is, right, so this is like a secure computation of this database query. And this is something that Google actually does with its customers. And this has been public for the last few years that Google uses secure computation to do this. They have some papers even about their techniques that they use. I think this is my last example. A few years ago, the city of Boston wanted to answer the question, are the companies in Boston paying women and men the same salary for the same job? And no one knew how to answer that question because none of the companies wanted to share their salary information. So they actually used secure computation to bring together all of the salary information for all the companies, not all the companies, but many companies in Boston, and just do simple statistics, based on the gender and the other parameters of people's jobs. And so they did this in 2017, and they were able to generate a report showing different statistics of how much men were getting paid and how much women were getting paid. And I think they've done this every year since then, and they just get more and more companies to contribute to this effort. So again, this is a secure computation of simple statistics over combined data sets. All right. So those are some examples that you can that can help you put things in perspective when I'm speaking abstractly for the rest of this lecture. So now I want to talk about what it means to securely compute some function. It's important in cryptography that we define what we mean by security. So when we start thinking about this, we can start listing different properties that are important. We don't want the adversary to learn more than the output of the function. If the adversary learns the output, we don't want them to prevent the honest parties from learning the function. We don't want the adversary to force different people to have inconsistent outputs. We don't want the adversary's inputs to depend on the honest party's inputs. We can make a list like this, but the list will be very long. And then we might worry that maybe our list is incomplete. Maybe there are some important security properties that we don't capture on this list. So we don't actually define security by this long list of properties. We do something completely different. And this is called the real world, ideal world paradigm. So I want you to imagine an ideal world. Here's two parties. There's Alice and Bob. They have their private inputs. They want to compute f of xy. In this ideal world, they just send their inputs to a trusted third party. That third party computes the function and just tells the result to Alice and Bob. And then the third party goes away and erases x and y, and it's completely trusted to do the right thing. So now let's imagine, so that's the definition of the ideal world. Let's think about what a corrupt party can do in this ideal world. Well, if you are a corrupt party, almost nothing happens in this world. You can choose an input y, and just by definition, that input has to be independent of the honest party's input. You can learn f of xy. You clearly don't learn anything else in this world because f of xy is the only message that you receive. And you can cause the honest party to learn f of xy. You can't cause the honest party to learn a different thing because this trusted party will only give the correct answer to the honest party. So this ideal world is very simple, and an adversary cannot really do anything harmful in this ideal world. So we will define security by saying that the actual protocol interaction is just as good as this ideal world interaction. And so in a little bit more detail, we'll define the protocol to be secure if for every way to attack the real protocol, there's a way to have the same thing happen in the ideal world. But we know that the only things that can happen in the ideal world are harmless. So that means the only things that can happen against the protocol must also be harmless. It's a very strange kind of definition. Even if you've seen other crypto security definitions before, you may not have seen definitions like this, and it's a little bit strange. So I want to fill in a little bit more detail about this kind of security definition. So I said that, every attack, you can have the same effect in the ideal world. So I need to be more specific about what is the effect of an attack. So here is a situation where the attacker is running the protocol against Alice, and I want to understand what is the effect of this attacker. Well, the attacker comes away from this interaction, and the attacker has seen some messages from the honest party. So the attacker has maybe learned something about the honest party's input. They can compute some information about the honest party's input. And they've also caused the honest party to give some output. And these are basically the only things that can happen. So the attacker can compute some arbitrary thing about the honest party, and the honest party finishes the protocol with some output. So those two things are the total, like the outcome of this interaction. So the security definition says for every real world adversary, and real world means the world where people are running the protocol. For every real world adversary, there is some adversary in the ideal world, I'll call it A prime, such that the combined output of the real world is indistinguishable from the combined output in the ideal world. So basically, if there's a way to learn something about the honest party and simultaneously influence the honest party's output, then there's also a way to learn the same thing and influence the output in the same way in the ideal world. But we're happy with anything that happens in the ideal world, so we must be happy with what happens here. So that's the flavor of this kind of security definition. And it turns out that instead of thinking about this ideal world adversary, it turns out that you should think about this other object called a simulator. So in this picture, I have this real world attacker, and it's the same real world attacker here. So this real world adversary thinks that it's participating in the protocol. Over here, it's running the protocol. Over here, in the ideal world, it's not running the protocol, but the simulator makes it look like it's running the protocol. And it turns out that this is enough to make the definition work. So a lot of times we'll talk about security in terms of a simulator. And just to give you some intuition about the simulator. So the simulator's job, it has two jobs. One is to send these protocol messages to the adversary, these thick arrows. They should look like messages coming from the honest party in the protocol. And the simulator has another job to figure out a message to send to this trusted third party, this message that I call Y. So the simulator looks at the messages that the adversary sends and tries to explain them in terms of some input Y. So if the simulator can really generate protocol messages that look like the real world, you'll notice that the only thing the simulator knows is f of xy. So if knowing f of xy, you can generate protocol messages that look like the real world, then the real world must not leak any more information than f of xy. And similarly, if the attacker is sending protocol messages that cause Alice to output something, then the simulator can sort of explain that effect by saying, oh, well, that's just what would happen. that's just what the honest party would output if in the ideal world you choose an input Y. So you can have any effect on the honest party that you want, as long as it's consistent with just choosing an input in the ideal world. Okay, I think that's it for the security definitions. Yeah, we make a distinction between two kinds of adversaries. The simplest kind of adversary is semi-honest adversary, and that means that the adversary follows the protocol as it's written. It doesn't deviate from the protocol, but it tries to look at this. It tries to look at these protocol messages and figure out something about Alice's input X in this case. So when we're talking about semi-honest adversaries, we don't have to worry about this extraction thing, because the attacker, we know that the attacker is running the protocol on some input. So we already know that the attacker's behavior is consistent with having an input Y. And so that's the effect that it should have in the ideal world as well. Okay, so because I only have a short time, I'm not giving you the full definition. If you want to know all the details of how to make a security definition for secure computation, you could check out this paper. It's 87 pages, and it's very complicated. So I only gave a simplified version here. So I've covered this item number 1. This might be a good time if you have questions about the security definitions or any of the concepts. Please feel free to ask them now.
Hi, Mike.
Yes. Somebody said something and now everyone is muted again.
Yeah, so I'm in the same room, so yeah, you just one homework. So could you talk about more about the semi-honest security on the infrastructure? And it's not very clear about. So you mean that in the semi-honest model, then there is no need to extract?
Yes, so that's exactly what I mean. We're trying to find a good way to, I've tried to find the right picture for this. So usually we think of an attacker as malicious. So this, imagine the adversary is malicious. They can send anything they want in the protocol. So they don't follow the protocol, they just send garbage. And if you send garbage to the honest party, you cause them to generate some output at the end of the protocol. So the job of the simulator is to explain, right? Remember, we're trying to say that it's not just what you learn from the protocol, but also the influence you have on the honest party's output. We want that to be just like in the ideal world. So in the ideal world, the only way to influence the honest party's output is to choose a value of Y, and then the honest party will get f of xy. So the simulator's job is to figure out what's going on with these, garbage protocol messages that the attacker is sending. But now if we know that the attacker is semi-honest attacker will never send garbage messages. They will follow the protocol and they'll send what they're supposed to send. The simulator will still need to send an input in the ideal world, but it's not a challenge for the simulator. It should be easy for the simulator because we already know that the attacker is running the protocol honestly on some input Y. And so the simulator just has to send that same input Y here.
Yeah. Sorry, I also know the difference between malicious security and the semi-honest security. So in semi-honest security, the Y is always the original one as the original protocol, right? So
yes.
So what about the extractor? What do you mean by the extractor here? Well, is it mean that the simulator needs to extract something, or?
Yes, maybe one piece of information that's missing maybe is if the adversary is malicious, then there may not be a well-defined input for the attacker, right?
Mm-hmm.
There's no such thing as an input for the attacker.
Yes.
Okay, so imagine I'm attacking you in the protocol. I don't even have an input. I'm just sending garbage to you.
Yes.
And then when we're done, you output some bit.
Yes.
Now we need to say the same thing must happen in the ideal world. I need to force you to output some bit.
Yes.
The only way I can force you to have output is by sending an input for me to the trusted third party, right? So I need to find an input that will cause you to output the correct thing, no matter what your X value was. So that's the simulator's job.
Okay, I got you. Thank you.
Mike, there are some other questions in the chats.
Yeah, I have the chat up. So there's a question. Someone says, bonjour tout le monde. That's nice. Somebody asks, is security in semi-honest equal to privacy? Yes. I'm trying to find a good slide. Yeah, so if we're in the semi-honest world, we don't have to worry about this honest party's output. So we don't have to worry about extraction. We don't have to worry about honest party's output. We only have to say that the view of the attacker can be simulated just only given f of xy, and that's only a privacy property. So I think whoever asked that question was correct. In semi-honest, it's only this privacy property. So that's only this distribution is indistinguishable from this distribution. Our protocols under the simplified definition composable. Yeah, so I'm not talking about composability very much in these lectures, but the way I drew it, it does reflect this composability definition. So if the simulator interacts with the adversary in the way that I drew it, so the simulator just talks to the adversary and sends messages back and forth like this, then you do get a composable definition. So composable means that if this protocol is secure, then I can run multiple copies of this protocol and other protocols at the same time, and it still remains secure. There are other definitions where the simulator it can talk to the adversary, and it can also rewind the adversary to an earlier state, right? So it can send a protocol message and see the response, and then it can rewind, reverse time, and then send a different first message and see what this adversary's response will be. That would not be a composable definition, but if the simulator works just by sending messages, this is called a straight line simulator. It just talks to the adversary but doesn't rewind the adversary to an earlier state, then you get a composable definition. Thanks for those questions. And let me know if it's still confusing. We can clarify. But I think this is a good time to move on to section 2. Right. So I want to describe Yao's protocol, which is probably my favorite thing in cryptography, I think. Yao's protocol for secure computation. So I'm going to start with something simpler. I'm going to call this a garbled truth table. So let's imagine that we're talking about two parties. There's Alice and Bob. They want to compute the function f on their inputs. And in this example, f is very simple. There are only 4 possible inputs for Alice and 4 inputs for Bob. And so I'll write the truth table of this function in this way. So here's the truth table of the function that we want to compute. So for each possible input, Alice will choose a random key. So A1 is like some random key, like a string, 128-bit string maybe. So A1 sort of, it represents input number 1 for Alice. And here's input 2, input 3. And there are 4 possible inputs for Bob. So there are 4 keys for Bob, and we label them B1 through B4. Now Alice will use these keys to, she'll use these keys as encryption keys, and she will encrypt this function output. So she'll use A1 and B1 as keys to encrypt f of F11. That looks like this. So I use this notation to mean encryption under both of these keys. The details of this encryption are not important because this is just a starting point. Okay, so we're still talking about what Alice does. Now she will randomly permute these ciphertexts. So you see now they're in a random order, and she sends these all of these ciphertexts to Bob. In this case, there's 16 ciphertexts. She sends them all to Bob in this random order. There is a step that I will skip for now. Remember, Alice has input X and Bob has input Y. And for each input X, there's a corresponding key, AX. And for each Y, there's a corresponding key, BY. Let's imagine that somehow Bob obtains these correct keys. So he has one of the A keys and one of the B keys. He has 16 ciphertexts. So what can he do? He can try to decrypt all of them. And when he does that, only one of these ciphertexts should open, right? Maybe X is 4 and B is 2. So if Bob has A4 and B2, he can try to decrypt all of these ciphertexts. Only one of them should work. And when he looks inside that ciphertext, he sees the value F of 42. That's the output that they wanted to learn, right? Alice has 4, Bob has 2. They should learn F of 4, 2. Okay, I want to argue that this protocol is secure. In this previous slide, I was showing you everything from Alice's perspective. And I think the important part about these MPC protocols is that Alice and Bob can have very different perspectives. So this was Alice's perspective. She knows all of the A's, she knows all of the B's, she knows all of these encryptions. This slide is closer to Bob's perspective. He sees a bunch of ciphertexts, but he doesn't know what's inside of them. He can only open this one ciphertext. So if we want to be more formal, we want to say that let's write down everything that Bob sees in this protocol. He sees all 16 ciphertexts. And this is how they are generated. He also sees A4 and B2 in this case. I didn't tell you how he learns those, but we will talk about that later. But this is everything that he sees. And I want to say that this view, Bob's view, can be simulated only given the output of in the ideal world. So in the ideal world, the output is F42, and we should be able to simulate this view only given that information. So I claim that the simulated view, so Bob's real view looks indistinguishable from a view where he just gets some random A key and some random B key, and one ciphertext that decrypts to the ideal world output, and then a bunch of garbage ciphertexts, so like dummy ciphertext, encryptions of a dummy value. And these two views are indistinguishable if you have a good enough encryption scheme. So I need an encryption scheme where an encryption of C under the keys A and B is indistinguishable from an encryption of something else, as long as one of these two keys is unknown to the distinguisher. So if you look at this first ciphertext, let's choose a more interesting one, actually. Let's look at this ciphertext. This ciphertext should be indistinguishable from a garbage junk ciphertext because Bob doesn't know the key A2. He knows the key B2, but there's one key that he doesn't know. So we need an encryption scheme where an encryption scheme that uses two keys. And if you don't know one of the keys, then that ciphertext looks indistinguishable from a dummy ciphertext, right? In most of these cases, Bob doesn't know either of the keys. But the point is that the simulated view can be generated using only this piece of information, this f of xy. So that means that the real view must not leak any more information than f of xy. Right? So you remember that's how we define security. Yeah, and I think this relates back to that previous question. I'm only talking about this privacy. This is just a simple privacy property. I will only talk about semi-honest security right now. Yeah, so I'm not talking about extracting anybody's inputs right now. So I'm just talking about the messages that are sent in the protocol. They don't leak any more information than f of xy. So that's the privacy property. Okay, so there is a problem with this protocol. You probably realize that when I described the protocol, I said, first you write down the truth table of this function. Well, the truth table of any interesting function is huge, exponentially large. So this protocol requires Alice to send an exponential number of ciphertexts to Bob. That's very bad. The other problem is that I didn't explain how does Bob learn the correct encryption keys, the keys that encode the real inputs. Okay, so I want to talk about how we fix these problems. So we fixed the first problem with the this is my favorite idea in cryptography. I described this protocol where you use keys to encrypt the final output of the function, right? That was the plain text inside of these encryptions. A better idea is you encrypt the keys to other truth tables. So here, using these keys for A and B, we encrypt intermediate values, which are keys, and then we use those keys to encrypt another table, and we can chain these things together. And that's what allows this to work. So I'm going to talk about this first idea, and then later I'll talk about how Bob learns these correct keys. It uses something called oblivious transfer. So we'll talk about that in just a second. Okay, so here's the real protocol for Yao's garbled circuits. Okay, so Alice and Bob agree that they want to compute this function of their inputs. So they write the function as a Boolean circuit. So here's a Boolean circuit with some gates and some wires. Every gate in the circuit has a truth table. So this function is an AND gate, but it has this. This is an AND gate. This is a bubble that means a negation, a little NOT gate. This is an XOR gate. So each of these gates has a truth table. And Alice and Bob want to evaluate this circuit on their inputs. So each of these input wires is a bit that belongs to either Alice or Bob, and they want to learn this output value. Okay, so every gate has a truth table. So I'm going to describe what Alice does. It's very important that Alice and Bob have different view of information. So right now I'll describe Alice's view. This is what it means to garble a circuit. So Alice will garble the circuit by doing the following. For every wire, she picks two values. I'll call them labels. You can call them keys or labels. I usually call them labels. These are used as encryption keys, but I call them labels. So on each wire, choose a different, two different labels, one with the subscript 0 and one with the subscript 1. And these labels will represent true and false on each wire. So I could rewrite the truth tables in terms of these labels. So A0 means false, B0 means false, and in this gate, false on both wires gives you a false output. And on the output wire here is the output wire with E0 as its false label. Okay, so this is what Alice is doing. She generates a label for each wire, and she can encrypt the truth table of each gate in the same way that I described before. Okay, so she uses A0 and B0 as keys to encrypt the value E0. And she does this for every gate in the circuit. And now for every gate, we have 4 ciphertexts, and you bundle all of those ciphertexts together and call that a garbled circuit. So a garbled circuit is all of these ciphertexts, 4 of them for every gate in the circuit. And this is what she will send to Bob. Okay. So instead of being exponentially large, now it's 4 times as, 4 times the number of gates in the circuit. Now let's think about Bob's perspective. If Bob knows only one value on each wire, you can think of that as an encoding of a bit on that wire. So I'll say this is a garbled encoding. So if you just know the value A1, that's like an encoding of true on this particular wire. So that's a garbled encoding. So if you have this garbled circuit, all of these ciphertexts, and you have a garbled encoding on the input wires, this circuit just has 4 input wires, and here is a garbled encoding of input 1001. If you have that information, then you can start to evaluate the garbled circuit. So let's look at this first gate. If I have A1 and B0, and I have these 4 ciphertexts, well, then I can only decrypt this third ciphertext, and then I will learn E0. I could do the same thing for this gate. So in this gate, only one of the ciphertexts can be opened. I will learn F1. And here I will learn G1. And now I have F and G. I can use them to decrypt this garbled truth table. I learn H0, I0. Okay, the important idea is that in the protocol, Bob sees a garbled circuit, all of these ciphertexts, and he sees the garbled input, this garbled input encoding. And the idea is that the only thing that's really possible is to evaluate the circuit in the way that I described. Because you can think of this invariant that holds. So the invariant is that if you only know, the invariant is that Bob should only know one of the two possible labels on each wire. So at each gate, if you only know one of the two possible values on the input wires of the gate, then you can only open one ciphertext, and then you will only learn one of the labels on the output wire. On the other hand, if I told you both I0 and I1, then you would be able to recognize that I0 is, let me back up. If you only see one of these labels, remember both of these labels, like think of E0 and E1, they're both generated uniformly at random. So Alice knows that E0 means false and E1 means true. But if I just show you E1, it just looks like a random thing. You don't know that it's the true or the false label. So when Bob is evaluating this circuit, he doesn't know whether he's holding the true label or the false label for any wire. However, hi, is there a question?
Yeah, I think there's a question. You can see that.
I don't see a question in the chat.
Okay, let me repeat. So
okay.
And you know that I only use A1, B0 of the third one instead of the first ciphertext for the first stage, for the first gate. Okay.
I didn't quite hear the question.
I can repeat. Sorry, one moment. It's in the chat. Can you see now in the chat?
Oh, now I can see. Yeah.
No.
How can I know that? How can I know that I only use A1, B0 of the third one instead of the first? Okay, so you're asking, how do I know that? How does Bob know to decrypt the third ciphertext in this gate? I think that's what you're asking. Yes, okay, good. Yeah, so that's what you're asking. So that's an important question. There is one step that I skipped. So if we go all the way back to this, this warm-up construction. So in this warm-up protocol, there's an important step where we randomly permute these ciphertexts. If we didn't randomly permute them, then when Bob goes through and he tries to decrypt all of them, he finds the one that he can decrypt. But if we didn't randomize the order of these ciphertexts, he would know just by the position, he would know that the input was 4-2, right? If the table really looked like this and he decrypted this one, he would say, well, that's the 14th item in the table is always for input 4-2. So that's why we randomize the order here. And I didn't really emphasize it when I was on this slide, but in this simulated view, you just pick a random position for this ciphertext. So that's something that's important, but I didn't draw it in this picture. So the garbled circuit should be all of these ciphertexts, but each group of 4 ciphertexts should be randomly shuffled. So I'm not shuffling them in my picture. And then Bob should try to decrypt all of them. And only one of those decryptions will succeed. So I hope that answers the question. actually, next week, I'll say more about garbled circuits, and it's very inefficient to try to decrypt all 4 of these ciphertext and then just check which one is successful. There's a way that you can tell Bob which ciphertext to decrypt without leaking information about whether this is a 1 or a 0. But for this example, I want you to imagine that for every gate, there are 4 ciphertexts. They are shuffled into a random order, and then Bob will try to decrypt. Bob knows that he has this key and he has this key. He'll try to decrypt all 4 of these with those keys, and only one of those decryptions will succeed. So I hope that answers the question. But yeah, that is important. Great. Okay, so the idea is that if you just see a garbled circuit and a garbled input, the garbled input is just, in this case, 4 different random strings. It doesn't tell you anything about the 0s and 1s. When you evaluate these garbled gates, you learn more labels for more wires, but each label just looks like a random thing. It doesn't tell you whether it's a 0 label or a 1 label. But usually we want Alice and Bob to learn the output of the circuit. So if Alice also tells Bob, if Alice announces I0 and I1 and sends those to Bob, and now Bob, when he decrypts, he sees I0, then he can say, oh, the circuit output 0. So the output of the function is 0. Okay, there's a question in the chat. How does Bob verify whether the decryption is correct? I'm not being very specific about that. You can imagine that this is like authenticated encryption or something. So I haven't given any details about this encryption scheme, and that's because yeah, I'm gonna give you all the details next week. So for today, you can imagine that this encryption scheme is authenticated encryption. So if you try to decrypt something in an authenticated encryption scheme and you use the wrong keys, you'll get some error message. So that's what I imagine in this picture. I don't want an encryption scheme where if you encrypt with the wrong key, you just get a garbage value, because actually even the correct ciphertext contains like some random value. So that's probably what you're asking. So yeah, I think it's maybe the easiest thing is to imagine that this is some authenticated encryption scheme. And it just, yeah, decryption gives some error when you decrypt with the wrong keys. Yeah, I'm not giving many details about that, because once we talk about the details of these garbled circuits next week, we don't have to worry about decrypting things with the wrong keys. It just doesn't, it's not relevant in the real garbled circuits, but it is relevant for this simplified example. So that's a good, everyone is trying to break this protocol, which is good. I think every time you see a crypto talk, you should be trying to break the protocol that the person is presenting. Okay. So that's the main idea of Yao's garbled circuits protocol, although I didn't show one step of it yet. But just this idea of taking a circuit and garbling the circuit and garbling the input is called a garbling scheme. So there's this paper from 2012 that gave formal definitions for this garbling scheme. So the first part that I showed you, which is what Alice does, is the garble algorithm. She takes a circuit, and then for every wire, she chooses 2 labels, and then she encrypts 4 ciphertexts for each gate, and that's the garbled circuit. She also generates this encoding information. So encoding information is just the 2 labels on each of the input wires. So if you have the labels on the input wires and you have an input to the circuit, then you can choose the correct ones and get a garbled input. So garbled input is just a single label on each input wire. And then in the protocol, Bob sees a garbled circuit and he sees a garbled input, and he can evaluate and get a garbled output. So in the previous example, garbled output is just like I0 would be a garbled output. And if you have the garbled output and you have both labels for all of the output wires, then you can figure out the value on that output wire, which is the output of the circuit, right? So if you know that the garbled output is I0 and you know both I0 and I1, then you can say, you can decode the output and say the output is 0 in this case. So this is kind of the more formal notation. You'll see if you read papers about garbled circuits protocols, they probably use this notation. And this notation helps us talk about different security guarantees. So the basic one is that if you see the garbled circuit, the garbled input, and the decoding information, then that reveals nothing beyond the circuit output. So just going back to this picture, if Alice sends to Bob all of these ciphertexts, that's the garbled circuit, and she sends, somehow Bob learns a garbled input, that's these 4 labels, and Alice also sends both I0 and I1, then Bob will definitely learn that the circuit output was 0, but he learns nothing more than that, right? So that information, this information can be simulated just given f of x. And I just also want to mention that nothing in this talk is nothing. It doesn't say anything about hiding the circuit f. We're not trying to hide this Boolean circuit. The only thing we're trying to hide is the inputs to the circuit and also the values on the wires. But the circuit itself is public. So that's why this definition says this information reveals, it can reveal f and it can reveal f of x, but nothing more. That's privacy. There are these other definitions. Obliviousness is kind of similar. An important one is authenticity. So I'm sorry to go back and forth so much. If Alice sends the garbled circuit to Bob and she sends a garbled input, then we know that Bob will learn I0 in this case. But if we don't tell Bob what I1 is, he should never be able to guess it, right? He shouldn't be able to lie and say that, oh, looks like I got the circuit to output a 1 instead of a 0. Right, so that just means, yeah, given the garbled circuit and a garbled output or a garbled input, it's hard to find any valid output wire labels except for, the correct, the wire label that encodes the correct outputs. So that's called authenticity. Sometimes that can be a useful property as well. There are other properties that we won't get into. You should just know that these exist, but we won't talk about these. Sometimes you want to hide what types of gates there are in the circuit. Sometimes you want to allow an adversary to choose inputs to the circuit after seeing the garbled circuit. So these definitions say that you have to first choose the input X, and then you get to see the garbled circuit. But in some situations, you have to give the garbled circuit first, and then the adversary can choose X. So you need a stronger security definition. Okay, there's a question. For each function we should design and transfer the garbled circuit, can we reuse a separate garbled circuit for any function? Yeah, the question about reusing a garbled circuit is very important. So I don't know if this is what you're asking, but I can see that in this circuit, there's two gates that are the same kind of gate, right? Both of these have the same truth table, but I still generate a different, garbled table for each one. And that's very important because imagine that we reuse this garbled circuit again on a different input. So on a different input, maybe we will have to reveal A0. So now Bob knows A0 and A1, and now he can open this ciphertext that he couldn't open before. And he sees that it contains E0. It contains the same thing as this ciphertext. So he knows that's false, right? Because in this truth table, the only thing that shows up 2 times is a 0. So yeah, I think it's important to say this, that these garbled circuits could just be used one time, right? If you use them more than one time on different inputs, then they will leak some of the bits. They will leak some of these input bits. If that's not clear, then I can maybe draw something on a different slide, but I think the question was about reusing garbled circuits, and yeah, the problem is that they can never be reused. Maybe we can go back to that a little bit later, if there are still questions. Okay, there's one last step that I haven't told you about. I haven't told you how Bob gets the garbled input. So here is a circuit. It has 4 input wires, and some of the input wires are bits that belong to Alice, and some are bits that belong to Bob. So if Alice is garbling the circuit, when she garbles the circuit, she chooses A0 and A1. She chooses B0 and B1, and she knows her input, right? Maybe she knows her input is 1, 0. So she can just send A1 to Bob and send B0. This is really easy. On the other hand, it's harder to get Bob's garbled input. So Alice knows both C0 and C1, but Bob knows his input. So he wants to learn one of these, but he can't just tell Alice which one he wants to learn. We need something that works like this. Alice inputs 2 wire labels. Bob inputs a choice bit, and he learns one of the 2 wire labels that he chose. And Alice should not learn which one he chose. So this is called oblivious transfer, OT for short. So if we have oblivious transfer, then we will be done with the whole protocol. I think I have a summary later, but if we have oblivious transfer, then we can let Bob learn the garbled input. Okay, so how does this work? So again, there's a wire in the circuit. Alice knows both of the labels, but this is an input wire for Bob's input, so he knows which label he needs to learn. So one way to do this uses public key cryptography. So Bob is going to generate 2 public keys, and he will know he'll have a trap door to one of these public keys. So he has a public key to PKC, but he generates the other public key in some way so that he doesn't know the secret key. So you need a public key encryption scheme with what I call a blind key generation. So there should be a way to sample something that looks like a public key, but you sample it without knowing what the secret key is. Okay, so Alice just sees 2 public keys. Bob knows the key to one of them, but Alice can't tell which is which. And so she just encrypts. This is now a public key encryption in this slide. So she encrypts the wire labels under these public keys. And now Bob knows the secret key to decrypt only one of these ciphertexts, so he can learn the wire label that he wants. So this is one way to do it. Everything that I'm showing you today is not optimized. The rest of these lectures are going to talk about how all of these steps can be optimized. But for this first lecture, I'm just trying to show you something that works, something that you can understand, but it's not the most efficient way to do this. Okay, so here is the big overview of the protocol. They both agree on a circuit, F. Alice garbles the circuit, so for every wire in the circuit, she chooses 2 labels. For every gate in the circuit, she generates 4 ciphertexts. She shuffles them randomly. She sends all of those ciphertexts to Bob. Some of the input wires in the circuit are Alice's inputs. So she can just send the garbled input for those wires. But Bob still needs the wire labels for the other input wires corresponding to his input. So to do that, they use oblivious transfer. So if there are n input wires for Bob, then they do n copies of oblivious transfer. So then Bob will learn a garbled encoding of his input. So now he has a garbled circuit, garbled encoding of X and Y, and he should be able to evaluate the circuit and get, the wire labels on the output wires. But Alice has also sent, all of the wire labels for the output wires, so he can look at what he learned and figure out which one is true and which one is false, only for the output wires. So he can compute the output of the circuit, and he shares that with Alice when he's done. And I think we argued that when Alice only sees the garbled circuit, the garbled inputs, and the output wire labels, he doesn't learn anything more than the circuit output, the ideal world output. That's what Bob learns. It's easy to see that Alice doesn't learn anything. Like the only thing she learns is this protocol message. It's just the circuit output. So it's easy to simulate Alice's view. She learns nothing from these oblivious transfers. Okay, so we're getting to the end of my slides. So I talked about secure computation. There are several parties, they have private inputs. They want to evaluate some function of their inputs. They want to learn the output of that function, but nothing else. And we talked about a few examples. I talked about how to define security. Security uses this real world, ideal world definition. So the protocol is secure if every attack against the protocol can be simulated in the ideal world. And then we talked about Yao's protocol, where you have like a truth table for every gate of a circuit, and you sort of encrypt the truth table in a special way. And then you also need these oblivious transfer steps to get the right values on the input wires. And once you have that, then Bob can evaluate the circuit blindly. Over the next few lectures, I'm going to tell you how to make all of this faster and more efficient. So the garbled circuits that I showed you today are very inefficient, and I will show you all of the tricks that I know about that can make garbled circuits smaller. So that's a special topic for me, because I have several papers about garbled circuits and how to make them smaller. So it's one of my favorite topics. So I'll show you all the tricks that you can use to make garbled circuits smaller, because actually, if we look at this protocol, this garbled circuit is most of the communication is this huge garbled circuit. So if we can make it smaller, then the entire protocol gets much more efficient. I will also, so that's next week. And then after that, I'll talk about this oblivious transfer step. Oblivious transfer is useful in lots of different secure computation protocols, not only Yao's protocol, but many other places. And it's very expensive because the way I described it, uses public key cryptography. Everything else in the garbled circuits is using symmetric key crypto, but the oblivious transfers use public key crypto, so that makes it very expensive. So I'll show you a trick to make oblivious transfer actually very cheap. And then the last lecture that I will give is if we know that we're evaluating a specific function, then we can design a whole protocol just for that function. So Yao's protocol will work with any function because you can evaluate any Boolean circuit. But if you know that if your favorite function has a really expensive Boolean circuit, then you can design a special purpose protocol just for that function. And so I'll talk about protocols for set intersection, which are some of my favorite applications of secure MPC. I think that's yeah, it looks like that's my last slide. So I know we have some time left over, and yeah, I want to make sure everyone has a chance to ask the questions, especially if anything was confusing. Good, and looks like there's already a suggestion. So I'll talk about what happens if we reuse a garbled circuit. I think that's very important. So I'm going to go back and I'm going to find just one second. So I have this other program where I can draw some things. So I'm going to take a screen. Oh, shoot. Sorry, I want to make this bigger. And I want to take a little screenshot. And I'm going to paste it into my little application. And now I can draw. And hopefully this works. Okay, so I want you to imagine that, yeah, this is the garbled circuit. I'll call it capital F. And let's imagine that, I'll try to make it consistent with what we had before. So let's say Bob knows the garbled circuit, and he knows the highlighted wire labels. So A1, B0, C0. So I'm just going to highlight what can he decrypt. He can decrypt this ciphertext and get E0. He can decrypt this ciphertext and get F1. He can decrypt C0, D1, He learns G1, E0, H0, I0. Okay, so that's what he learns. Okay, yeah, I think we are comfortable with that. So what if we use the same ciphertext and now we try to evaluate it again on a different input. So now the input is 1 0 1 0. So so this is still the same. This is the same. Okay, now I have C1 and D0. What's that? Maybe this doesn't work very well. I haven't thought about this yet. So we can learn G0. Oh, but I can also decrypt all of these, right? If at this point I know C0, C1, D0, D1. So I can decrypt all 4 of these ciphertexts. Now I know G0, G1, and F1. So basically I can decrypt those 2. And I'll still just learn H0. That's the same. Yeah, so in this case, so these are all the ones that can be decrypted. But now there's a problem here, because if we look at, Bob can decrypt all 4 of these. So Bob decrypts all 4 of these. And so he knows that he can see that these 3 are the same. He knows that the truth table must have been 0, 1, 0, 0. Even if these 4 ciphertexts were shuffled, he sees that these 3 were the same and this one is different. And so he knows that he can know that G0 must be false. G1 must be true. So he learns the meaning of this bit in both executions. And he can also conclude that, so this was C0, D1. He must also know that, like, he can conclude from the truth table here. I think the truth table was, like, in this case, is 0, 1. There's only one combination that gives true on this gate. So he can figure out that C0 must be false and D1 must be true. So there are some things that he can deduce. So he learned, so because we reuse these same ciphertexts but revealed more of the input labels, we leak the value on these wires for this example. For a different example, you'll leak different information. But here on 3 different wires, Bob learned the value on that wire. He's only supposed to learn the value on the output wire. Somehow I closed my chat. Oh, there's a Q&A window. Okay, that's why I didn't see the question the first time. Sorry about that. I only had the chat window open. But now I don't have it open, so I need to open it again.
There's another question, whether is encoding, the encoding of Bob's input is necessary or not? Right.
Okay, so I can see that now, because the evaluation is on Bob's side. Yeah, so the important invariant here is that Alice should know both wire labels, and Bob should know just one of them. And that's the important invariant that should be true for all of the wires. So Yeah, I mean, I think I understand the question. It's a reasonable question. Let's use this. It's true that Bob knows his input, so it's weird that we have to give some extra information, even on those wires. But Bob needs more than just his input, because C0 and C1 are like encryption keys. He can't guess them. Alice chose 2 encryption keys. Bob will never guess one of these encryption keys, right? And we can't, yeah, if I were to change, let me make a new picture here. So I think your question is saying, like, don't have these wire labels. This is Bob's input to the circuit is here. Let's not use these wire labels. Let's actually just encrypt using just the bit 0 as the key. And let's encrypt using, the bit 1 as the key. I mean, maybe that's what you're thinking, but I hope it's obvious that you can't encrypt something with a single bit, right? So there needs to be, something needs to be encrypted with a key, and Alice needs to be the person who chose the key. So there has to be some encoding. You can't just encrypt something under a bit 0 and a bit 1. Bob can just imagine that he has a 0 one day and then imagine that he has a 1 in the next second, and he could open up all of these ciphertexts, and then the same bad thing would happen. So you want to restrict Bob to open just a single ciphertext. That means things have to be encrypted with real keys that Alice chose. So there needs to be some encoding process. Okay, but does not Bob always know C0 is 0 and C1 is 1? Yes, good point. So the question is, maybe for this example, if this is these are Bob's input wires, he does know that, yeah, in this case, he knows that this is a 0 and he knows that this is a 1, because those are his inputs. And so he'll also know that whatever gate this is, he knows that this is a 1. But from Bob's perspective, like, these are Alice's inputs, so he doesn't know what's on this wire, and he won't know what's on this wire. Yeah, that's a true observation, and in this circuit could probably be simplified. So I present a very general version of Yao's garbled circuits. It treats Alice inputs, Bob inputs all the same way. I think you are correct that in this example, if Bob knows both of these input wires, maybe just make this thing an input wire, right? Bob computes this part in his head because he has all of the inputs to this part of the circuit, and maybe we should make this an input wire. But yeah, it's true that, yeah, but the first time that there's a gate with one of Alice's inputs coming into it, the output of that gate will be unknown to Bob. But yeah, that's a very good question.
Okay. With another question, can we apply garbled circuit to privacy-preserving federated learning, especially secure aggregation? Do you think it would have good effects? That's from the machine learning community.
Right. So you can use the garbled circuits protocol for any function, but the cost of garbled circuits depends on the size of the Boolean circuit. So so let's take the problem that you want to solve. Imagine writing that as a Boolean circuit. If that Boolean circuit is huge, then garbled circuits is maybe not the best choice. There are many other secure computation protocols, and they have different trade-offs. So usually I say that if there's something that you can do very efficiently in hardware, then garbled circuits will be pretty efficient, because hardware is similar. It's a similar architecture, right? It's writing something as a Boolean circuit. So in principle, you can use garbled circuits for anything, including federated learning. In practice, maybe federated learning is more about arithmetic operations like multiplications, divisions, additions, and those operations may be more efficient as an arithmetic circuit, and there are better protocols to support arithmetic circuits. The problem is there's just too many secure computation protocols. It's very hard even for the experts to know which is the best one for any particular application. But yeah, I do want to stress that garbled circuits protocol is general purpose. It will work for any Boolean circuit, but some problems have huge Boolean circuits, so it could be inefficient.
Next question: is there any useful tool for our algorithms that to convert a function into a circuit, Boolean circuit, I guess?
Yeah, there are several papers that they have tools for generating garbled circuits, or tools for generating circuits that you can use for this garbled circuits protocol. You can use hardware design languages like VHDL, hardware design languages, and they can generate circuits. In garbled circuits, you'll see that it turns out that these kind of gates are free. Well, not that one. These kind of gates are free, and these kind of gates are expensive. And so you can tell the hardware design tool that you can tell it that these are free, and so try to minimize the number of these gates. There are people that build tools to do that. There are some, if this person is really interested in the question, they can send me an email and I can list some specific papers. I don't remember the names right now, but there are some papers of tools that can generate these circuits. There are also some high-level languages, like you write a program in C, and then the compiler generates garbled gates on the fly. So there are tools that do this as well. You don't need to have the entire circuit all in one place to do this. You can generate the circuit as the program is running. So that's also possible.
Okay. So if you are interested, please send an email to Mike. So he will reply you with more details.
Yes, and if you can spell my last name, then you can find me on the internet. Yu has my email address too. There's a question about passive into active secure. Only the receiver learns the output. Transform active secure, only need to be secure. Okay, so this is a question about semi-honest versus malicious. And there's a question about if only one person learns the output, then do we need to worry about both parties being malicious? I think the answer is you need to worry about both parties being malicious. It doesn't matter who is getting the output. So even if I don't get output, I can still behave maliciously and mess up the computation. and you still need to worry about that in the security proof. So unfortunately, you don't get any benefit to just having one party learn the output. You don't just get to ignore malicious security problems in that case. Yeah, if the receiver is adversary, yeah, if the person getting the output is corrupt, you still worry that they learn more than they're supposed to learn, right? And even if the person who gets no output is corrupt, maybe they learn more than they're supposed to learn. Maybe they force the wrong output. So you need to worry about those things. So.
Okay, so the timing is perfect.
Incredible. Yeah, I'm very grateful for those questions so that we could we could fit the time perfectly.
Thank you for the very educational lecture on the simulation paradigm and the garbled circuit and oblivious transfer. And we look forward to the concrete instantiation and optimization of the garbled circuits in the next talk. Probably yes. one week from now, or we can negotiate, agree on.
Okay. Okay.
Actually, today Andy Yao is around, so I believe he will be very happy to see a poster about his protocol. Okay.
Yeah. Well, if you have Andy Yao walking around, I don't know why you would invite me, but. But yeah, that's fantastic. Yeah, so we can schedule the next session.
Sure.
But yeah, I look forward to seeing you all again next time. Maybe next week, maybe in a few weeks.
Can discuss. There was another.
Okay. Thanks, everybody.
Thank you. Okay. Thank you, Mike.
Okay. Bye.
Bye.